In this part, I thought we would talk about counters, and in the particular case, what I have on the breadboard is a 74LS90 decade counter. The functional diagram is down below. I have it set up at this time to work with the pulsar that I showed in part 1, but it's a little bit hard to see what's going on with a something like this where you're having to watch 14 pins at once. But basically what this counter does is it has a by 5 counter and a by 1 or by 2 counter, so it can count up to 10, or actually 0 through 9. We'll look at that in a second. As you apply clock pulses, you see it goes from all zeros to a 1, and then a 2, and then 3, 4, and so on. In other words, what this counter is doing, if you remember from part 1 when we talked about binary arithmetic, it's basically counting in binary from 0 up to 9. When it gets to 9, it automatically goes back to 0 on the next clock, and that's the reason why that it's called a decade counter. Decade meaning by 10 or in tens. But in order to show you a little more about this, what I would like to do now is to set up this same counter using the analog discovery and show you how this operates under dynamic conditions, and I think it'll make a little more sense that way. So on the screen is the analog discovery. In this case, I'm using the original analog discovery, or analog discovery 1, as it's sometimes called. I could have used the analog discovery 2, but I have it set up on another experiment right now, so it was more convenient to use this one. On the left over here, you see the waveform generator, which is generating a square wave at 1 kilohertz. And by the way, I should point out that there is a trick here. Unlike Dave Jones, I don't think it's just for young players. I think it's for all of us, because I'm certainly no young player and I fall for it all the time. The way that the wave generator specifies its output is actually in peak mode and the offset. So in order to get a signal that goes from 0 volts to 4 volts, which is sort of a standard TTL input, you have to say 2 volt amplitude with a 2 volt offset. In other words, you notice here there's a 2 volt offset, and the total amplitude is 4 volts away from 0. Just point that out in case you've been caught by it. If you're like me, you'll get caught by it again, just as I did a minute ago. On the right is the oscilloscope of the analog discovery, and I'm going to zoom in a little bit so you can see a little better what's going on. At the bottom is the input clock. In other words, it's the waveform that the waveform generator is generating. And you'll notice that there are each division I have set up to be exactly 1 clock cycle. So there, from the start, when it starts out in the 0 state, there is 1, 2, 3, 4, 5, 6, 7, 8 clocks, and then this, the yellow, is the high output. Now, it only stays high for a short period of time. Let me show you by changing to 2 milliseconds per division. You see that after 8 clock pulses, and in this case, now each division represents 2 clock pulses. Then it goes, the QD output goes high for 2 clock pulses and then back low. In other words, what it's doing is it's counting 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Or if you want to start at 0, it's counting 0 through 9. Now let's look at the logic analyzer for the analog discovery, which is up here. And this one, let me reset the display so that it shows up a little better. The bottom trace, and this is the logic analyzer, the bottom trace is the QA output of the decade counter, the LS90. The next one up is the QB, the next one up is QC, and the last one is QD. Now, let's begin at this point and call this time 0. At that point, the decade counter is all zeros. Then it goes to a 1. Then it goes to a 2. Then to 3, that is 2 and 1. Then to 4. Then to 4 and 1, which is 5. Then to 4 and 2, which is 6. 4, 2 and 1, which is 7. Finally it goes to 8. And then it goes to 8 and 1, which is 9. And then you'll notice it resets all back to zeros again. That is the basic operation of a decade counter. So next, I'm going to give you a little bit of an overview of how some of these logic elements, the sequential elements, are used in digital computers, and then I'm going to shift gears and talk a little bit about design philosophy and other things. Here is a very simplified diagram of how a modern digital computer is organized. Now, not all of them are built this way, but this is the most popular and widespread. It's named after a scientist named John von Neumann, and it's called the von Neumann Architecture. Basically, the idea is that there is a memory in which are stored both the program and the data. There is a program counter, and the counter we just looked at, slightly different one, but nonetheless the same basic principle is used to select the place in memory that the current instruction is being fetched from. So the instruction stored in memory is fetched and is placed in an instruction register. Then logic, using this instruction, decides what else to be done inside the computer. Now there's some pieces that are missing, input, output, and so on. But the arithmetic logic unit that we looked at earlier, that contained, if you remember, a shift register and a latch, as well as an adder, and of course in modern computers even more. But basically, this is the structure of many of the computers that you see today. Now, obviously, there have been many improvements and changes and other architectures and so on. But the idea is to show you how you can interconnect a series of these fairly simple sequential building blocks to make a very complicated and very useful digital computer. So now I'd like to move on to talking about the process of digital design. These are some of the steps that design engineers normally go through in producing a digital design. Whether it's a stored program computer or a modern cell phone, it's pretty much the same process. Generally, a specification is developed which has to be complete. In other words, it has to do everything that needs to be done, and it has to be clear. In other words, everyone working on the project has to be able to understand it and know what needs to be done. A development plan is then developed in which you have to choose the technology. You have to make sure you have measurable goals in the plan. In other words, make a good computer is not a goal. Make a computer that will execute 6 million instructions per second, that's measurable. It has to have a timeline. And you have to decide on the staffing and other resources that go into this. Finally, there needs to be an implementation plan. And that means you have to be able to measure, to know if you're meeting the goals, review the status of the process, and prepare necessary revisions. Designers use a number of tools. Early on, you saw how that logic can be simplified, and there is simplification software. Some of it based on the Quine-McCluskey or similar methods. There also are state tables, which we'll look at in a minute. There are state reduction software that we'll talk about in a moment. Then usually timing diagrams that meet certain timing rules. For example, propagation time, setup and hold time, the bus speeds, the clock rates. And finally, there is the packaging and interconnect problems, where you put the various parts and how you route the signals between them, what the various spacings and trace sizes are, and so on. And testing, thermal, and other EMI, FCC rules, UL approval, and so on are always a part of the design process, and there are tools to do that. For example, there are pre-compliance testing tools that will let you find out if you can meet the EMI or FCC specs and so on. One of the things that are useful in digital design are what are called state tables or state diagrams. This is a state diagram. The larger circles represent states. In other words, stable time windows or places where the circuit remains for a period of time. In a clocked logic, the state transitions, that is, moving from this state to this state, are done by means of a clock. In asynchronous logic, which we aren't going to talk about, the state transitions occur because of other things and are not clocked, and therefore they're not synchronous. It's a very complicated process, and that's one of the reasons that we're not going to talk about it. But in clocked logic, for example, this simple D flip-flop with a very simple exclusive OR on its inputs, we'll go through this state diagram. They're very useful. They can be a lot more complicated, however. If we look at this circuit, still not a terribly complicated circuit as designs go today, but the state diagram for that circuit can be rather complicated, and this is simply, remember, a 2 flip-flop design. Imagine one with 1,000,000 flip-flops. So state diagrams, there's a lot of software to help you minimize state diagrams and optimize your circuit for those. But another thing that you have to worry about are timing diagrams. Timing diagrams show the timing relationships between all the various signals. They're not as simple, however, as this diagram, complicated though it might seem, because it's not just how these things line up, but in the real world, these signals have times associated with them, and the times are some of the things that are very hard to work with because the times vary. They vary based on the process used, on temperature, on voltage, and other things. And so various things like the length of time it takes a signal to go from a 0 to a 1, called rise time. Many problems with that. One is it can move around. The second is the faster it is, the more complicated the design becomes. And the reason is that in modern designs, you have a series of requirements that the chip designer specifies for the particular chips you're using. things like the setup time and the hold time for flip-flops and so on. You have to take all of those things into consideration when you do digital designs. Now, that whole process takes place in a design environment. And I've listed here a few of the rules of thumb that I have found useful. Some of these I thought up and others I stole from others, from smarter people than me. One of them is the idea that all conductors are transmission lines. You really need to think in terms of the speed of the signals as well as the length of traces and other things. Just thinking in terms of a DC circuit with a battery and a light just won't work, because the rise times of modern circuits make virtually all the conductors a transmission line in one way or another. The next thing is, everything is an approximation. You may measure a voltage as 5.00 volts, but it's not really 5.00 volts. If you carry it out far enough, you'll find it's just close to 5 volts. The next thing is, digital is really analog. In other words, although we call it digital logic, everything is really analog until you get down to the sub-microscopic world or subatomic world when you get into quantum physics, but we won't go there. Another thing is, you have to think about testing during the design cycle. It is a design issue. It's not an after the fact. In the early days, they used to talk about throwing a design over the wall. What that meant was the designer was done with it and now it was somebody else's problem. Well, that just doesn't work anymore. The next thing is, nothing will ever precisely fit the specification. You need to have some judgment. It has to just be close enough. And that's the reason why that, unlike physicists, engineers are constantly dealing with the fact that what they are doing is not absolutely precise. It just works. All designs will require changes in manufacturing, and that's an issue that a lot of young engineers never realize until their design crashes in manufacturing and the head of the company comes into their office and says, "Why is this happening?" No plan survives completely intact. You don't want to change a plan arbitrarily, but you also don't want to be so wedded to it that it can't be changed when you know it needs to be. People are human. You have to deal with people, including yourself, and we all have personalities. Engineers are people. Life goes on. Let me now show you a few of the books that I have found useful in design over the years. I don't include the Diagnostic and Statistical Manual of Personality Disorders, but that probably should be at the top of the list. One of the early books that I found useful in learning how to work with analog circuits, remember I said digital is analog. You really need to know a lot of what's in books like this. By Robert Pease, Troubleshooting Analog Circuits, and it's a collection of articles that originally appeared in EDN magazine. He worked for National Semiconductor. It's a very good book. I recommend, if you can find a copy, get it and read it. Obviously, you're going to need data. This is a TTL data book. Obviously, TTL is old school, and most of the modern stuff is done using CMOS and enhanced versions of metal oxide semiconductors. Nonetheless, a data book is essential. There's a lot of data in there that, if you know it, you'll do pretty well. This is a text that I used in college many years ago. Introduction to the Logical Design of Switching Systems. I'm sure this one is no longer available, but a good book like this that gives you the fundamentals can be very useful, even in the day of computer-aided design, where a lot of the design is done for you by the computer. This is a book on electronic packaging and interconnect. This particular one is by Charles Harper. There are others in this general idea or line. You don't need to know everything in here, but you do need to have a general understanding of packaging and interconnect before you can do a decent design these days. This is one of the best books on the actual problems of high-speed digital design. He calls it a handbook of black magic. It's by Howard Johnson and Martin Graham. If you really want to know the nitty-gritty details of high-speed digital design, including the impact of fast rise times on circuits, this is the book for you. This book is a very good example of some things that are available on the used book market and contain a lot of useful information. This particular one is by James Buchanan, CMOS TTL Digital Systems Design. It's just filled with all kinds of interesting information. And finally, this book that was published, it's by, I never have been able to figure out how to pronounce this, Bakoglu, on circuits, interconnections, and packaging for VLSI. That's a very large-scale integration. Once again, the particular books you use aren't as important as that you know what's in them, which means you have to read them. And reading these books is not a fun evening, but if you want to be a decent design engineer, you really do need to have an understanding not just of the digital circuits you work with, but of the entire physics and environment in which digital designs work. So I've run on a little bit longer than I expected here, but I do hope that this will give you a little bit of an idea of what you need to know to become a decent digital designer today. And I think at this point I'm going to stop working on this particular series. But perhaps in the future we'll pick up and do something further. At any rate, I hope you've enjoyed this, and I hope you'll stay tuned.